Quick question before we get going here. How many people here are more on the mechanical side versus the electrical side? Who's a mechanical designer or engineer? Who's on the electrical side? Okay, awesome. Well, this is more tailored to mechanical product designers, but we're going to cover a wealth of information that's really applicable to everybody. Just the majority of our channel, it's a mechanical channel. Solidworks historically is a very mechanical product, and there's a lot of companies that are facing challenges with the emergence of electromagnetics in the market in just about every industry. And that's why we're here today, to talk about electromagnetics and how they're driving the product design of tomorrow. And are you prepared for that? What do you need to do to be prepared for that? So we're going to cover some things. We're going to do a brief introduction to electromagnetics. Then we'll talk about what it means for product design now and in the future, and what we can do to get ahead of it. And then we'll touch on simulating electromagnetics, some of the different capabilities we have at Dassault for simulating EMAG. And then we will review a couple of customer stories. Depending on time, we may shorten a little bit of the customer stories in there, but hopefully you guys enjoy it, and I'll be available for any questions at the end of this. So, electromagnetics. It really is everywhere. And years ago, it was much less prevalent, but every year we're seeing it in more and more industries. And in today's life, electromagnetics touches just about everything we do, from the tools we use to the systems we use to the vehicles and machines that we use. It really is everywhere. And it's a fairly broad topic. It covers a very broad spectrum of applications. We could be talking about starting with low frequency or no frequency down at the sensor level, doing sensors and DC stuff. As we start increasing and adding frequency in there, we get into low frequency applications like motors, like generators, etc. Moving into higher frequency, we start getting into communication. What typical high frequency applications would be like RF communication, microwave communication. We're talking antennas. And even further than that, we move into the photonics spectrum, into the terahertz range. And if we can simulate light as an electromagnetic wave, or if we can treat light as an electromagnetic wave rather than the particle, we can simulate it. And there's some really neat things we can do all across this spectrum, and it all falls under sort of the broad umbrella of electromagnetics. So why is it important to us as product designers? And I'll briefly mention, I'm a mechanical engineer. I've been around for, been an engineer for just over 20 years now, been using Solidworks for just over 20 years, and my background is purely mechanical product design. Now, the last few years, since I've joined DS, I have focused on electromagnetics because it is such an emerging industry, and it's really starting to touch more and more. And it's at the heart of transformation in just about every industry out there. Things like smart health, smart buildings, smart energy, smart transportation. We can pull up some statistics on that, and then there's too many from too many different industries to really cover, but medical electronics is one thing. Patient monitoring and patient care tools are growing over 7% a year for a compound annual growth rate. In 10 years, they're predicting electronic systems will represent 50% of the price of a car. Half of the price of a new car is going to be electronics. So, what does that mean for us as product designers? Well, here's a decent example of the type of integration we're seeing right here. Does anybody know what that is? Yeah, it's an E-axle, specifically. That's an electric drive axle. That's an Allison transmission, eGen 100D. What's important about that? Well, it puts out a huge amount of torque and a huge amount of power, 35,000 pound-feet of torque and about 885 horsepower out of that package. So, what does it mean to us? There's a lot of more connection between these mechanical and electrical worlds now, and products are becoming much more connected. Electrification in general is sort of transforming industries, and how is it doing that? Well, you've got things like this, a perfect blend of mechanical and electrical design, where you have a really beefy mechanical system, you also have a ton of sensors on there. You have integrated high-power electronics. And some other trends, miniaturization. We've seen this in mechanical, and the exact same thing is happening in the electrical world. Things are becoming smaller and smaller, denser and denser, which leads to more challenges for placement, for interference, for thermal management, etc. And that brings about reliability and safety concerns. Now, we'll ask some questions here. Some questions that I know a few years ago, before I got into electromagnetics, I probably wouldn't be able to answer. So, where should you place an antenna to perform best? Are you confident your design will pass EMC testing? Will you have thermal issues that you need to manage, or signal issues, or power issues in your design? Finally, are the emissions from your device safe? Now, these are all concerns, and if you had to answer these today, would you know where to start? Well, let's summarize some of these challenges for a moment. Now, as I mentioned, a big one is antennas. We have, and we'll touch more on this later on, but placement of antennas, performance of antennas, interference between antennas are more and more important in a connected world. And as connectivity kind of increases, so do the challenges around it. With that comes interference and signal integrity problems as well. Needing to make sure that these systems function properly and data transmission is effective, especially at high speeds. Then we get into EMC, EMI, and safety regulations. And we'll touch more on that later, guys, but we're talking about emissions from devices. Whether your device might interfere with other devices, whether it can accept emissions without causing interference in your system, and of course, the safety that comes with those emissions. And heat issues and energy efficiency, again, are always a concern with electronics. The densification and miniaturization is really driving that. And another big challenge for us as product designers is material selection. We're used to selecting materials for structural concerns, for fatigue concerns, for longevity, for thermal things. How many of you guys are used to selecting materials for electromagnetic performance, or how these materials may apply with, play with antennas? Some, yes, but a lot of people, it is still quite new. And one of the things we'll talk about now is how to integrate mechanical and electrical design. And we really need to break some of the silos that are present in a lot of companies right now. Now, some of the problems that we're seeing and why traditional product design is not going to work too well in the future is separated mechanical and electrical teams. When they work in silos, and that's very often the case, and then you try and sort of combine systems at the last minute, you end up with unforeseen issues. You get these late stage compliance issues, and when those changes happen late in the design process, we know, whether it's mechanical or electrical, late stage issues are expensive, and they very often delay time to market. Now, another thing is these separate tools. Looking at just electrical or electromagnetic systems or just mechanical systems with separate systems means you're not looking at the complete picture, and you can miss pieces of that puzzle. And finally, regulatory compliance. There are a lot of compliance regulations out there worldwide right now, but there's more and more emerging ones as well, specifically around emissions and human safety. So where do we go from here? What can you do to stay ahead as a manufacturer or a designer? Well, it starts with simulating electromagnetics early. For the compliance that I was just talking about, we can use predictive analysis, not to pass those compliance tests. Virtual compliance passing is not a thing yet, but being able to get ahead of it so you know when you send your design out for compliance testing you're going to pass, that's very much a thing, and it saves a huge amount of time and money. We can prevent thermal problems by actually simulating the mechanical systems and the electrical systems at the same time and simulating cooling solutions for those. Now, the other thing you can do is try to get collaboration between your mechanical and your electrical teams. It's usually not the same people doing those designs, but you can work closely together right from the start of a project. And finally, the way to succeed is really optimizing designs and materials, not just for structural, but structural and electromagnetic performance. And how do we do that, guys? Well, it's simulation, simulating electromagnetics. And to do that, there's a wide range. If you guys remember that spectrum we were talking about from DC to daylight, there's a lot of very different applications. And I'll just briefly touch on them, but we're not going to focus on all of them today. We'll focus on the key ones. So to start with, low frequency. This is the same sort of frequency spectrum we were looking at earlier, but in low frequency, we can get issues like sensors, capacitive and inductive touch sensors, reluctance sensors, Hall effect sensors, all sorts of position, speed, location sensors. We get into high-powered magnets that can be used for things like imaging machines, MRI machines, even steering particle accelerator electron beams. And finally, electric motors as well. That's a big one. We're not going to touch on motors too much today. You may see a little bit as we go, but let's talk about high frequency for a second. I mentioned that was essentially communication. When we talk about classic high frequency, we're talking about antennas. Not just the design of antennas, but the placement of them, how they work with other antennas, how they work mounted on a platform. And there's more. Of course, microwave design, RF component design as well, passive filters, things like that, circulators, diplexers. But another big one we will focus on today is electronics. And that's such a broad topic. We're talking about essentially embedded electronic systems and PCBs and the components on those. And when we talk about that, we're interested in the signal integrity, the power delivered to the components, so power integrity, EMC and EMI, which is all about emissions and compliance, and of course, thermal issues and safety and compliance as well. And a little more exotic, but we are actually seeing a lot of traction in this realm right now, charged particle dynamics. We can simulate a huge range of charged particles with our software, and that can be used for things like in the semiconductor manufacturing industry, looking at basically sputtering and etching and semiconductor plasma reactors. That could be looking at particle accelerators and actually steering and tuning the steering and focusing of electron beams in those, as well as X-ray and vacuum tube components, actually some defense weapons as well. There's a lot of things that can be in that realm. But today, we're going to focus on three main topics. We're going to focus on antenna design and placement. We're going to focus on electronics in general, and specifically safety and compliance. These are going to be the biggest issues facing product designers in the next 10 years. Now, at DS, how do we handle this? On the right, you see just a subset of some of the applications here, and some very different ones, from aerospace applications to radar applications to electronics applications, human body safety, a whole range of things. Do we solve them with a single solver? We don't. CST actually has 25 different solvers in there. There's 4 main ones, as well as a number of different niche solvers. Well, not even niche solvers, specific solvers. And combined, they can handle just about that entire electromagnetic spectrum. Now, some of the sort of key selling points, this isn't a sales presentation on our software, but it is an educational one. I do want to tell you some of the technology that we have. So again, those 25 different solvers, and it's not just 3D electromagnetic design. We can simulate circuits as well. If you have circuits that are driving your design, whether that's filtering circuits, amplifying circuits, things like that, you can do co-simulation of your circuit schematic with a 3D design, and then even take that and move it into a multi-physics thermal analysis. Some of those 25 solvers, there's a built-in FEA thermal solver, as well as a full built-in CFD solver for e-cooling solutions, specifically tuned for electronics cooling. Now, another thing about this, full integration of mechanical CAD and electrical CAD, and we'll touch on that a little bit more later and sort of the breadth of that. And finally, high-performance computing. And I'm not just talking about sort of HPC clusters. We have some great tools you can use for local and cloud solves in this. CST supports GPU acceleration in a lot of its solvers, which can lead to some massive enhancements. In fact, we did some benchmarking with NVIDIA last year, and their latest workstation GPUs, we're seeing accelerations. I don't have a slide in here for it, but they benchmarked versus a 64-core machine versus that same 64-core machine with one of the new NVIDIA workstation GPUs. Double-digit, more than 10 times enhancements in just about every study. Some studies accelerated up to 60 times faster with the addition of a single GPU to those 64 cores. So we need to take advantage of that technology, and you can locally. If you have that technology or horsepower locally, you can use it, but we also offer it on the 3D Experience platform. And this solution, it's really the same solution, whether it's on desktop or on platform. But if you are on platform, you get access to the public cloud. If you don't have IT infrastructure, but you're still solving really challenging problems, you can go in and run this on 16 cores embedded all day. On the cloud, no charge. If you need more than that, we offer high-level CPU and coupled CPU-GPU solving. You can solve with up to 288 cores, or even up to 48 cores and 8 GPUs concurrently. And when you do that, you can take some of these solution times down from hours to minutes. And that allows quick iteration, quick change management, and ultimately faster time to market. Now, let's talk a little bit more about this, and we'll jump into antennas specifically, the first of those areas. And there's some things that are driving our basically antennas being more pervasive everywhere. And 5G is one of those things, but a big driver for our industry is Industry 4.0, smart plants. We're talking about connected robots and robotic equipment in plants that can communicate with each other and control networks. And of course, the domestic Internet of Things as well. Your connected watch, your connected dishwasher, washing machine, all of these things that 20 years ago, nobody could think about an internet-connected washing machine, but they exist. Now, what are we talking about when we talk about antenna analysis? What are we trying to do? Well, we're trying to simulate how that antenna performs, and we're trying to do it as quickly as possible. And you'll see a bunch of examples up here, a blade antenna, we've got a little monopole antenna, a mobile phone with a number of antennas in it, little antenna, an array dome, and even an array up there, a phased array that we'll talk about in a moment. But there's something important about all of these. Except for that array that's sort of standalone up there, if there's a common thread between the rest of the antennas on there, it's that they're mounted in an environment. Analyzing antennas as a standalone device is completely useless, or near completely useless unless you're optimizing the antenna, because they are so sensitive to changes in their environment. What they're mounted near, what's beside them, other things that may be interfering with the signal or affecting the signal, let's say, not necessarily interfering. So we need to analyze them mounted. Now, what's an example of this? Let's take a look at this excavator. This is basically a front-end loader, and we need to put a GPS antenna on it. Well, where might we put that? There's a few different locations, and as a mechanical guy, one of the first places I might look at is right there in that little sort of recessed pocket on the back. Makes sense, it's protected from damage, but it probably doesn't have great line of sight. You might get reflections, things like that. So what about top dead center on the device? Well, super clear line of sight, but it's vulnerable. So a trade-off might be up at the top, good line of sight, but then put a protective cage around it. But again, any sort of protective cage, any structure, conductive structures especially, near an antenna can lead to issues. So what does it look like from a performance point of view? Well, clear differences in those. And again, you see sort of the nasty looking far field in that recessed location. There's some reflections and a lot of things leading to sort of lobe differences there. The top location looks like we think it would, a fairly smooth, uniform far field. And then we get that top location with the guard bars, which is almost a trade-off between the two. Now, it's not the only way we can visualize that. Looking at what we call far field plots, we can also look directly at the electric field created by the antenna. And here, it's pretty clear what's going on. You can see some of the reflections in that first image, and over on the side, you get those dead spots there. Obviously, that is the cleanest, best signal. Whoops, sorry, right in the middle. And over here, if you actually look, that's a cross-section of those two little steel guard bars, and you can see the shadows those predict up to the left and up to the right there. So out of those, that's the kind of decision. I'm not going to say which one of these is best. It's really going to depend on what you need out of the application, but these are the type of challenges we will need to face. Now, another thing to mention, just to make you guys aware of, is arrays. And arrays are interesting, and they have a lot of applications these days. This is where we actually have a lot of very small antennas placed together, working in conjunction with each other. And you can do some really neat things. You can actually steer these in terms of directivity and receiving as well. And it's an interesting process, but we can handle it. We have tools, and I mentioned those different solvers. Different solvers can be used for different parts of this. You might start by optimizing the individual element. Well, then you might look at that as a sort of infinite array and see what the effects might be. Then put it into a discrete array. And once you're in a discrete array, we can use different solvers, full wave solvers, to actually look at that through different scanning angles, analyze different code book requirements, etc. But there's more to just placement of antennas. What about interference? If we look at a system like this, and that is, I believe, a Global Hawk drone, we actually have up to more than 10 antennas. That's not all of them, but what happens when you have 10 different antennas on a platform? That could be this, that could be a drone, that could be a cell phone sometimes has that many antennas, etc. How do you predict whether they will work well together? That's an interference task. Now, what we can do here, just to show you guys a quick example, we'll look at two different antennas. We've got a transmitting antenna, which is a VHF antenna, and then a GPS receiver mounted in front of it. Now, they operate at very different frequency ranges. We're somewhere, call it 150 megahertz for the VHF that's transmitting. The receiver, way higher than that. We're at 1.5 gigahertz. You would not expect those to interfere with each other, right? They're like an order of magnitude apart. And yet, they do. And the reason they do, what you're seeing there is an interference matrix of sort of looking at unfiltered performance for all of those. We see quite a bit of interference, but specifically on that one, and it's actually caused by harmonics. All of these antennas, they radiate not just at their intended frequency, but also you get harmonic resonances at multiples of those. And it's the 10th harmonic of roughly 150 megahertz is about 1.5 gigahertz, and we can see issues in there. We have automated tasks to go in, once those antennas are placed, to run those type of studies, and then you can do things like add filter networks and things like that to get that interference under control. So really, it's all about optimizing performance, solving placement challenges, preventing interference, and ultimately speeding up the development process, because that iteration takes time, and you'll hear from one of our customers later today about that. Now, let's move into the next area, which is electromagnetics. Electronics and PCBs. Well, there's some interesting stats on that, and what's driving a lot of this is embedded electronic systems, and they can be found in just about every industry, transportation, mobility, aerospace, medical, just about, there's so many embedded electronics these days, and depending on the industry you're in, they can be a huge amount of the challenge we're facing. In the automotive industry, they actually account for 80% of innovation, 50% of the total certification cost of a car, and 80% of the complexity of the design process. So what do I mean when I say embedded electronics? It's not just the board. There's a lot of other things in there. Of course, we do have the board, but what about connectors? What about vias? What about cables? Things like that. There's a lot more we can look at. We have a complete tool set to look at this. Sorry guys, give me 1 second. And it starts before we even lay out the board design with looking into technology investigation and sort of optimizing components and bits that might go on that board. But the real fun starts once you have a layout. And to start with, importing that layout. And you'll see in another slide, but we can import just about any ECAD file out there, any sort of EDA file that you have, if it's Cadence, Altium, Zukin, Mentor Graphics, we can bring it in directly, natively, with the full detail, every trace, every component, every via on that board. Then we can use the design checker built into CST, and this looks at some basic design rules to prevent issues for SI, PI, as well as electromagnetic compatibility challenges. And it helps do a first check on things to get rid of some bad oops mistakes right off the start. Well, one of the other things we'll look at is what we call signal integrity. And as we transmit signals, we need to make sure the signal that's being received is the same one that's being transmitted, or at least can be detected that way. All signals degrade a little bit, but can the zeros and ones we're sending be reliably picked up as zeros and ones at the other end? Power integrity. Well, we talked about the densification of electronics and all of the different components on these boards. They all have very stringent power requirements, and we need to be able to check that that power is being delivered correctly and that we're not getting issues like ground bounce and impedance mismatching, etc. Well, then we can actually look at thermal simulation. If you run a power integrity study and you find out the thermal losses in the components as well as the traces in the board, we can take those losses and directly transfer them into a thermal simulation as heat sources, right within the same software. All of this is without ever leaving the same window, guys. And finally, moving into what we call EMC compliance checking. And this is looking at the radiated emissions and basically looking at a virtual EMC EMI test lab. Now, how do we do this in a little more detail? Well, to start with, combining the mechanical and electrical CAD. Well, the nice thing with CST, you don't really need to worry about that. We can integrate just about any MCAD and just about any ECAD out there. CST has been around for over 30 years, well before Dassault purchased them, so we're kind of CAD agnostic. We don't care, I mean, it's awesome if you're using Solidworks, but if you're not, or if suppliers and vendors are using something other than Solidworks, we can bring in just about every mechanical CAD file type in there. We can also bring in, as I mentioned earlier, just about any type of ECAD file, bring them in natively, combine them, and analyze them together. Let's take a quick look at power integrity for a moment. So this is looking at that game controller again, and there's some power requirements in there. Not a ton, but we have a USB port up at the top of the board, and that actually comes down to a voltage regulator, and some of that gets sent off to a battery, some of that gets sent to an integrated circuit that is right there, and we can actually zoom in specifically on that IC and see what the voltage levels are going to it. And it's very, very small voltage drops where we're talking like a millivolt in there, but what's important, we can very quickly go down and define, we can see the power at every single pin on that chip and find out whether or not it meets the tolerance that we need on it. And in a nutshell, that's power integrity. For signal integrity, again, I mentioned that was all about making sure the signal that's received is the same signal that we sent. And there's various ways to do that. This is a USB 2 signal that we're looking at here. And to start with, how do we actually get the USB 2 signal in there? Well, we have we support what we call IBIS files. And IBIS files simulate the performance of integrated circuits. They're basically telling us what data, what series of zeros and ones, at what intervals are coming out of that chip. Now, to start with, when we look up there, that blue and orange graph you see in the top right, the blue one is our transmitted signal. The orange one is our received signal. So there's obviously some voltage drop as we go along, but it's not just voltage drop we're looking at. Ultimately, what we're looking at is something called an I diagram. And this is basically, this is the signal as it goes between a 0 and a 1 and back down to a 0. Ideally, that would be a square step function, but it's not. There's rise time, there's fall time, there's jitter, there's all sorts of different discrepancies in there. What you're seeing in the center, that purple shaded region, that's what we call the SI mask for USB 2. That's the requirement to meet the USB standard to make sure that all those zeros and ones are being recognized correctly. So in this case, we are outside of that I mask. We're okay. Now, I mentioned thermal as well. Once we go in and run the power integrity study on this, we have a great idea of the losses all over that board. We can directly, in the same package, run a thermal study on that. And again, built-in CFD solving specific to e-cooling, and we can go in and get very accurate ideas of what the temperatures are, not just in the board, but also in the mechanical components, also in the airflow that's moving around it, etc. Now, the last thing we'll talk about is compliance and safety. And I say last thing, before we get into some case studies. But this is a big topic, and we'll start with EMC, EMI compliance and radiated emissions specifically. What you're looking at is an EMI test lab. And this is where you, well, I'll just bring up the stats to start with. This certification is mandatory. If you have a consumer electronic device, you need to pass. In the US, it would be FCC regulations. Various places, other places in the world, they have their own local and regional and some emerging global regulations as well. But the most important thing here, you cannot bring your product to market until EMC requirements are met. And the tough thing with simulating electronic systems is there's so much that can affect EMC, EMI, that you really, like trying to physically test that before you have a very nearly finished prototype is really hard to do. You need to wait until your system is almost in final state. And at that point, if you fail, you're almost certainly going to have months of delays to try to figure out what that problem was, and you're probably gonna miss your launch date and be late going to market with it. So what are we recommending? Are we talking about just don't do the physical testing, just do virtual testing? No, they do different things. And physical prototyping, you can simulate entire systems, all the effects, but you only get a pass-fail out of it. If you are above the required, or above the allowable limits at certain ranges, you then have to figure out what is actually causing that, or what combinations of things is causing that, and that's often like physically decimating a system, taking pieces out, turning pieces off until you find out what drops it. Virtual simulation, it's different. It can't give you the required certification, but it can give you insight. You can look at individual parts or the system as a whole. You can separately run analyses very, very quickly to identify what the problem is, troubleshoot that design, and get the confidence that when you go to market, that design is going to pass the first time. And we'll hear that from a customer in a few minutes. But it's not a replacement for physical testing, but it is a huge complement to it. So let's look a little bit more at what the workflow might look like for that. Well, if we take this game controller, for example, what we can do, the way the EMC test lab works, you basically have a very large and sensitive antenna there, and you have to test your product basically at its maximum power limits and find out how much power it is emitting. Now, it's not just in a single orientation. You have to try that in every possible orientation in there to find out if you're exceeding those limits in any direction. Well, we can simplify that significantly. We can run in, and we have automated EMC workflows where we can say, place probes every X degrees around the part at a 3-meter interval. If we're looking at the FCC 15B Class 3B emission standard, which is the consumer electronics one, that would be a 3-meter sphere that you're seeing right there around the part. We can run all of those orientations in a single test. Now, what actually happens? Well, if we look at the signal plot up here, what you're seeing, those big square signals, the red and the green ones, a USB trace is a differential pair. So you're sending a positive signal down one trace and a negative signal down the other trace. And you see the smaller, sort of nasty looking lines between them, those are the received signals in there. Again, they don't rise quite as high. They have some overshoot, there's some undershoot. There's a bit of time delay as well. But generally, what you're seeing, if we look at the electric field, that signal actually couples to a lot of other areas on the board. Wrong button there. So we're going from sort of the top there, it's just along that USB trace, to down there at the bottom. But look at the light ups on the other areas of the board. This is actually causing some resonances and some excitation in other areas of the board. But what we see in the bottom right, that is a radiated emissions plot, and you're seeing the FCC, what I just said, the FCC 15B, Class 3B, 3-meter, that's a mouthful, limit lines plotted up there. We are currently under all of those. We would pass that EMC test. But that's an ideal circuit. What if we did just a slight delay on that? Signals can be delayed by a lot of different reasons, unequal trace length, issues in IC performance, things like that. But what if those signals were just delayed by 25 nanoseconds? And you can see up there, there's a very slight delay between the top signal and the bottom one there. Well, we now get into something we call common mode interference. And if we look at the ideal case versus a case with a 25-second time delay, we're seeing a lot more excitation in there. And all of a sudden, we're actually failing the FCC test at multiple different points. Anywhere we exceed that line, and this is over the frequency spectrum, guys, on a log scale, but anywhere we exceed that, even one of those would fail that test for us. So this is the type of analysis we need to do to find out if we're going to pass compliance testing. And why? Because if you fail it, you're going to delay your launch. You're looking at months of redesign. So that's the regulatory side of compliance. And I mean, this is also regulatory, but also a little bit more important to us maybe. Is it safe? Is your design safe for whoever's using it? And what we're talking about here is non-ionizing radiation that's emitted by any electronic device. And the main risk here, we're not talking radiation like gamma radiation or things that can affect DNA. The main risk is tissue heating. If tissue gets heated when it's exposed to this sort of non-ionizing radiation, normally, and that happens when you put your cell phone up to your head, when you are wearing a smartwatch, etc. Normally, the power levels are low enough and the blood flow pulls enough heat away from the skin that it's not a concern. But when you get into higher powered devices or things that have to be in contact with you for a long time, this can be a concern. You can end up with burns and all sorts of tissue damage. And what we look at for that are sort of two things. For the human body side of it, specific absorption rate. That's the measured value of how much RF energy is being absorbed by the body. And then in high-powered applications, we sometimes look at just field limits. What's the allowable exposure levels for workers or public? For example, working on 5G towers, and often requires things to be de-energized and big warnings about the field levels and things like that. How do we deal with it? Well, I'll tell you that in 1 second, but I will say these are also governed by various different regulations, and this is an emerging market. We're seeing new regulations pop up for this all the time, and the thing is, they're different, and nobody agrees on them. The standards you might see here in North America might be different than the ones we see in Europe, might be different than ones we see in South America or Asia, etc. And they are constantly changing. There's new ones coming out, there's ones being obsoleted, so just because you passed compliance last year in one geo does not mean you're okay this year in that geo or any other geo, really. Now, how do we deal with it? We have built-in safety workflows. We can run specific absorption rate studies, and we could do it with that game controller for hands on it. How do we do that? Well, we have a built-in biomodel library within CST, and these are fully detailed human body models as well as sort of silhouette models as well. They're fully posable, and we can directly calculate that. And I'll show you guys a quick example of that right now. I think I have to manually play this video. Do I? No. Okay, so this is an EASO device. This is basically a fake device developed by DS, demonstrator device, not a fake device. This is a wearable Bluetooth-enabled IV pump that can be used for IV therapy, and it has a bunch of different parts inside it. It was designed in Solidworks, and essentially it delivers medication like an IV pump does, but it does it with wireless communication back to the doctor or nurse that can control the flow rate, look at different parameters, etc. Well, we can bring that into our software, and here's our human body models, and you'll see we're going to put this in a human arm. This has fully detailed blood vessels, bone, skin, fat, muscle, etc. And we can run that and find out what the absorption rate is on that arm. In that case, it was too high. We can put an absorber in the SolidWorks model. It's a block of metal that sits behind that antenna. Just by doing that, we can make sure we meet the SAR limit. But as we do that, it's going to affect the antenna. We put a big block of metal behind it, it suddenly detuned us. We're off frequency and we don't have nearly enough return loss there. We can add a built-in matching circuit to sort of change that impedance and bring it back to performing. Very, very quickly, we can get that to a point where it is right on frequency with a very, very strong return loss. So that's a case of answering in one study what are the human safety implications and the antenna performance implications, because it doesn't just have to be safe or perform, it has to do both at the same time. So the summary for that, guys, compliance readiness. There's more and more regulations out there. There's more emerging every day all over the world, and getting ahead of that helps save a huge amount of time and money, helps you get to market faster. It gives you insight that you just can't get from physical testing, and safety is not optional. It really is mandatory in, from an ethical point of view as well as a regulatory point of view as well. So at this point, that's sort of my overview of challenges and solutions that we have. Let's take a look at some customer stories in this. And we're going to start with one, which is Inovonics. You guys may have seen this. If you actually look, we have some customer-facing videos and interviews available where they were one of our champion customers last year. We did an interview with them because they were so successful with our Electromagnetics product. And what they do is antenna design for a range of different industries, and it's not just antenna design, it's product design, but using our software specifically for antennas. And they focus on a bunch of things, from senior living to commercial security systems, as well as submetering, a lot of submetering. And if you don't know what submetering is, let's say you have an apartment complex with one water main coming into it, then it distributes out to a bunch of different units in there, and you want to be able to track how much water is being used by each individual unit. You can put one of Inovonics submetering systems in there, and you don't need to wire these in. They all communicate wirelessly. Everything Inovonics does has antennas in it. So what sort of challenges do they face? Well, to start with, detuning of the model. We mentioned how antennas are very, very environment dependent. What happens when you place this inside a standard electrical box in a wall or next to electrical cabling? Placement of the antenna within that device, as well as just being able to visualize performance and getting insight that you just can't get from a single test or a single point probe on things. And we'll talk all about that. Now, as we start, we'll talk more about the SolidWorks integration. So, of course, most people here, SolidWorks users, we can start directly in SolidWorks and save this to the 3D Experience platform. And again, this is the platform-based workflow. It doesn't have to be. If you guys can't use cloud or don't want to use cloud, the desktop solution functionally is exactly the same without the cloud performance. But we can very quickly save that out to cloud and then load it into CST. And I'll probably skip over the antenna design process for now. It is a big process to sort of find the right type of antenna, do the initial calculations on it, but most of the time is spent sort of in the middle section there, which is simulating an antenna, prototyping it, making sure it works, and then iterating that process till you get it right, and then you end up with a final design. Well, let's talk about the next thing, which is proximity and how proximity of different materials affect performance. To start with, the base antenna versus the antenna with just a PCB added or a galvanized iron electrical box around it. Again, visibly very clear. We get a lot less signal strength, a lot less performance once this is put in this big metal conductive box. Now, there's some things we can find about that as well. It's not just the overall performance, it's the directivity. On the left, you see very uniform front and back performance. On the right, well, that box has completely killed any sort of antenna performance around the back of it. You can kind of see it silhouetted in there. We project very well forwards through the plastic cover, but not backwards. And that's something you have to keep in mind during design. You can't just place one of these in a center wall in the house and have it connect to things on various sides of it. So the other thing we can do is look at location positioning, and different solvers for this. We use what we call an asymptotic solver. It uses a shooting and bouncing rays method to predict antenna performance. And I mean, I could talk to this, but visually, the graphics do a better job than I can. You can very clearly see differences from line of sight and looking at one antenna in various locations in the room versus two antennas. And in this case, the only way to get clear coverage in that room is with two antennas. Anywhere else, you get some pretty significant dead spots and shadowing spots. Now, the final thing is packaging constraints. Inovonics is limited to the size of a standard electrical box for a lot of these parts. Now, you do have some choice of what you can move in there, but not very much. They really have to take advantage of every bit of performance they can. Part of that is standing off the PCB, using little standoffs on the screws to be able to push that out just 5 millimeters further than it was. You can already see the difference in there. Pushing that out just a slight bit, less than 1/4 of an inch out, leads to much improved performance on the antenna. So that's the kind of things they are looking at. And one thing I would encourage you guys, if you're interested in this, to go watch the webinar. I'm sure if you search Solidworks Inovonics, you'd be able to find that on YouTube very quickly. There are some benefits that they talk about that we just don't have time to cover today. Benefits of the 3D Experience platform, being able to collaborate with other people, being able to use this on any device, taking advantage of the cloud computing I was talking about earlier. And it really gave them some nice benefits. And you can hear Mark, their lead engineer, talking about it. To start with, being able to use it anywhere, any device, anytime, through the platform and the cloud. The high-performance cloud computing helps them iterate much, much faster than they're able to using local resources. And the platform provides improved document control and communication. But that's kind of what it does. What does it do for them? Well, seamless collaboration between the stakeholders, between the designers, the engineers, the manufacturers, and the management. It lets them get really fast results on very complex models with no overhead at all. And it makes they're always using the latest revisions of designs. They're able to share those designs, communicate better, which leads to faster decisions. And ultimately, what it's all about for Inovonics is getting to market faster with these designs. Now, you've heard it from me, but let's hear it from Mark Zackham, who is the lead designer, lead antenna engineer at Inovonics. No, this is the one I have to play manually. One sec.
We have realized not only a huge impact in our revision time. We're going from 4 to 5 revisions on the RF side to 1 to 2, which is months of time saved, which is incredible. I have the ability to work on almost any device because of the cloud infrastructure. So I can work off my iPad, off my laptop, off my PC, almost anywhere in the world. I just need a good internet connection. And I don't have to worry about any power or any like horsepower to run these simulations because I can use the online cores and online features that we have to run anything I need. We have perfect dock control. I understand all my revisions. Everything's saved online. I can grab them off of one device and throw them on another without any concern. And all of this is to just accelerate design and make sure that the only thing you have to worry about is being an engineer and not worrying about the softwares that you're using.
So, straight from a customer on how these tools are helping them stay ahead. Now, we're near the end of our time here, but I do have another short story I can run through with Cargos. And is anyone here familiar with Cargos? If anyone's here last year, you may have seen these guys up on main stage. Pretty impressive customer. What they do, they design these small, what they call compact logistic vehicles. Now, this is for first mile and last mile delivery. They're not designed to replace trucks. They are designed to do basically the final delivery or pickup and taking to a transit point. They're filling a real gap in the market, and they're out of India, but man, this has the potential to take off so many places in the world. They wanted to design a small scooter with a massive cargo capacity, 225 liters and 120 kilos of cargo in there. Now, they had, and you can find lots of information online on this, but they used our 3D experience platform and our ModSim approach to look at not just the electromagnetics of this. They looked at structures, they looked at aerodynamics, they looked at battery cooling, rider comfort, etc. But we're going to focus on two things they did, which were making the vehicle connected as well as compliant. Now, again, I mentioned all the different things they were looking at. They did a lot of different studies to do that, and we'll see that as we go here, various different study types, but again, we're going to focus on the electromagnetic side of it. So let's talk about the antenna placement. Now, these need to be essentially trackable. Part of a logistics network, of course, is knowing where your delivery drivers are at any time and being able to schedule them accurately. So they need GPS. They also need connectivity to cellular networks. Now, in this case, we're looking at GPS antenna placement and optimal placement on that device where they can get a good GPS signal all the time without interference. Well, a few things we can touch on. Now, I won't touch much on the cloud data access. You guys are aware we can, I think every SolidWorks customer is aware now, we can save to cloud. We can pull down from cloud into other pieces of software. You're aware it's integrated with SolidWorks. Talk about some of the things that really help them. One of our meshing techniques that we call octree meshing with efficient automatic cell lumping can take some of these massive models and automatically make them much, much easier to solve. And it does this by keeping the mesh really, really fine where it needs to be. But as you move out into very large areas away from sort of detail, where you're in consistent material or consistent fluid, we can lump those cells. And we can take mesh sizes down sometimes in the order of 90 to 95%. Of your cell count can be reduced, which leads to way faster solving. It's not about faster solve times, it's about what that gets you, which is faster iteration and a faster path to the best design. Now, in this case, you'll see some of the cloud computing that you can use as well. If you are using the platform, we can save this to the platform, and once it's there, we can very easily run this on any sort of cloud compute configuration that we have available to us. So we'll see that in 1 second. This is the simulation manager in a browser. I can go in, click simulate, and then pick what I'd like to run on. In this case, maybe 4 GPUs, 24 cores, and 168 gigabytes of RAM concurrently, and run that. Now, once it runs, those results are basically seamless. It's just like solving locally. You get your results, you can very quickly access them, and you can iterate and run those again. And you can even use the platform to pull up those results on any device. If I wanted to, I could pull up results on my cell phone right now, or a tablet, or a laptop in an airport if I'm missing a designer view because I'm traveling, etc. Now, the other thing this lets you do is very quick design updates. So if we tried out different antenna positions in here, we might want to move it from one side of the dashboard to the other, or maybe mount it underneath a cowling or panel on there. You can change either by just mating something or changing configs in SolidWorks. Whoops, let me go back one more time. Oh, and I can't fast forward that in frame, but we'll see it in a second. You can very, very quickly change those configurations. It's as simple as once you save that model to the cloud again, when you open the model in CST, our electromagnetic software, it will prompt you. It will say this model is out of date. Press F7 to do a parametric update. Press F7, boom, you have your new geometry immediately. You don't have to set anything up. Again, you click run, you get your new results. So we can see that here, and we can very quickly compare different designs and get the best performance as quickly as we can. Now, that's how Cargos kept these designs connected. They were able to easily use the cloud to get their data and run. They didn't have to do any import-export process between different files. The meshing made this very fast, and the cloud computing made this very, very quick to also fast. And they were able to find the optimal design Now, the final part of this, and I'm kind of going to burn through this because we are over time, guys, is compliance and safety compliance. So again, we're looking at specific absorption rate, that SAR value we were talking about. Now, there's various ways we can do that. You guys saw the human body model, but it wasn't super impressive. It was just an arm, a very detailed arm. Well, we have a poser for those models as well. What if we need one of those detailed models riding a scooter? We can do that very quickly with our poser interface. And that's as simple as basically loading in your model. And we sometimes do this as silhouette models. In this case, we don't really care about the internals. We can do that very quickly, pose this into any different orientation we need, and then incorporate it into our model. And that's what lets, and we have a various range. You can do different body types, different heights, you can simulate children, men, women, pregnant women, infants, even there's some animals in the biomodel as well, lab rats and things like that. You can get the results you need. And then what they've done, I'll just jump through the end result there, they can find out exactly what the compliance is, and in that case, the main area where you might be concerned about SAR is on the hand of the rider, right on the hand. So we'll finish right here, guys, with a summary. Electromagnetic challenges are really growing across every industry. We know simulation is essential to get ahead of those challenges, and we have some really good tools to do it. And compliance and safety are going to be two of the biggest challenges that we probably haven't come up against as mechanical designers that we will in the future. And the way to do this is be proactive. Don't wait till you have problems. Get ahead of these challenges now. Talk to your SolidWorks partner. They would be very happy to come out and facilitate a demo, find out more about your specific needs, and show you how we can help. So that's it, guys. Thank you. I hope you've got some insight out of this.